Okay, so if we go over to Canvas, if we look at files, you'll see a folder name under Unit 1, Slides. Okay, and so this is the PDF we're going to be using today. But just a lot of people last semester did that. They would download the slides and then take notes on them. You can do it electronically, or you can do it kind of old school with paper. Okay, and then you have two assignments that are going to be due next week. One's a lab waiver and a life safety contract. Those need to be PDF files, so you're going to download them under Files. You go to Admin, and you'll see, you won't go to Lab, you go to Lab Related, sorry, and you'll see the lab safety contract, and then down towards the bottom is the waiver. So download those, sign them. You can do it totally electronically, but it needs to be a PDF file. And then you're going to click on the assignment, and it'll prompt you for a file name. Then you upload it. The easiest 20 points you'll make all semester. Okay, so does that make sense? Now, when you look at this, I have 3 units. That's because last semester I had 3 units. This unit, I've split those up to be more granular. So there's 5 units this time. Now, that's the good news on that is you have to study for each test less material, because the material gets very detailed. You have to study less material, and you get an opportunity to recover from a bad test grade as well, because there are more tests. Okay, all right. Last time I mentioned the project, and I mentioned again in lab. Does anyone have any more questions about the project? Yeah. If you go to, yes and no, if you go to project up here under files, these are a bunch of examples I've uploaded over the years. And there's a rubric and blah, blah, blah. But, you just kind of click through some of these and get an idea of depending on the bandwidth. Some of these files are kind of big, I guess, like this one, for example. But it's going to be a 3-panel poster and then a 1,000-word essay. And I'd recommend doing that over the recess, semester recess. Man, massa prisa. Now, this is an okay one. This one probably got a B. There's not a lot of chemistry in it. We are in a chemistry class, so I expect your project to involve chemistry. But anyway, I mean, I recommend a black background on your poster board, so if you have an option. And the reason for that, the pictures really pop. The white background, they kind of blend in. But anyway, go through those. You'll see lots of examples. Normally, there's a book written, in fact, it's an introductory chemistry textbook. It's called Chemistry is in Everything. And it's really true. You look around the room here, we've got plastic bottles, very chemistry. We even have what's in the plastic bottle, very chemistry. So usually I can relate anything of interest for you with a chemistry slant to it. So anything you're interested in, whether it's music, sports, explosives, we can relate it. Okay, so All right. Are there any other administrative questions? Okay, let's jump into content then here. Okay, now yesterday we introduced at the end of the hour hydrocarbons, and there are three kinds of hydrocarbons. There are alkanes, single bonds only, alkenes, single and double bonds, and alkynes, single, double, and triple bonds. So we're going to focus on alkanes today. They're the simplest. Now, people always say OChem, organic chemistry. Now, if you look it up online, frequently it'll say it's the chemistry of carbon, which is partially true. It's definitely chemistry of carbon. But it's also the chemistry of oxygen, nitrogen, hydrogen. And our bodies, now this is a whole allied health slant, this class. You're going to see a ton of oxygens. You just look at glucose, one I drew up there on Tuesday. It's got 6 oxygens in it, 6 carbons, 12 hydrogens. So that oxygen carbon interaction, there's a lot of chemistry around that, because sometimes you can do a double bonded oxygen, sometimes a single bonded oxygen. So organic chemistry is really the chemistry of carbon, oxygen, hydrogen, and nitrogen. There are extremely huge numbers of organic molecules, hundreds of millions of them. Inorganic chemistry molecules, like you did last semester in 305, they're much, much more limited. But organic stuff is like off the wall, and that includes the biochemical stuff, which is another, 400 or 500 million. So there's just a zillion of them out there. And there's certain traits about organic compounds. They tend to be covalently bound as opposed to ionic. They tend to be and this varies a lot. This is generally weak. It's not. It's for hydrocarbons, it's definitely weak. But for the rest of the classes of organic compounds, they vary from very high ionic. For example, organic acids are extremely ionic. That's why they easily dissolve in water. Alcohol, vodka. Vodka is half water, half ethanol, 2-carbon alcohol. So it varies greatly. So there's not generally weak is not, I always take exception to that. Physical state, they tend to be all over the place. Because they're generally nonpolar, they tend to have low melting points and boiling points. So they tend to be more gaseous than an equivalent molar mass of an alcohol, for example. Usually they're flammable, not all of them, but frequently flammable. In fact, some of the anti-flame retardants are organic, which obviously they're not. Those are not particularly flammable. Low soluble in water, because they're non-ionic, they're not conductive, except for the highly ionic organic compounds like acids, bases. Those are conduct electricity fine. And it says usually slow. Who's heard of TNT? Trinitrotoluene. That's an explosive. So is that reaction slow or fast? It's freaking fast. So it varies. A lot of reactions are slow, some depending on what the structure of what you're starting with. If what you're starting with is typically unstable, the reaction's fast because it wants to become more stable, like TNT. You know the guy that invented dynamite, got the Nobel Prize for that? This was just before World War I. And guess what they used the dynamite for? the Nobel Peace Prize. He got it for done. Yeah, World War One, the first wild war with machine guns, particularly. Okay, now yesterday we talked about line drawings, and again, so a line drawing has got an ending, a beginning, a beginning, end, and then frequently, but not all the time, a kink. Those are all carbons. How would you draw something with one carbon in it? For example, if we had methyl alcohol, this is what methyl alcohol looks like. If we made this into an alcohol like isopropyl alcohol. So some of your first dry labs are going to be practicing this kind of stuff quite a bit. Now, the space filling model is not used very much. They frequently will show it, but to me, it doesn't show much information. Ball and stick models are sometimes used. Most of the time, we're going to be using line drawings, particularly in the biochemical phases of each one of these. Now, the way this course is laid out is your unit 1 is going to have no biochem in it, but there will be biochem from unit 2 onward. Your hardest test is going to be unit 2. Over the last 15 years, and the reason for that is it includes carbohydrates. And carbs can be real complicated because the structures are complicated. Okay. We have isomers. Isomers are compounds that have the same formula, differing structure. And remember, when you're looking at a unique structure from one molecule to the next, if it's just a rotation of it, it's not a new molecule. It's the same one. Because when we get into, we're going to synthesize aspirin. It's one of the labs in here. And you're going to be analyzing your synthesized aspirin for things like purity and structure and all that stuff. And one of the things we talk about are the modalities of motion for molecules. And one of the modalities is tumbling in free space. Another is transport. Another is stretching. Another is wagging. There's a number of modalities that molecules move through until they become down to absolute zero. Then there's no movement whatsoever. So a isomer like this one here is C2H6O. And this one we did on Tuesday. So what is it? This is an ether. This guy is an ether. This guy is an alcohol. Bottom line is the formula is the same. Now, if you were given the formula C2H6O, and I said, well, is this an alcohol or an ether? Then you'd have to say, well, they're both equivalent structures as far as the Lewis structure goes. So how do you know which one it is? Is it the ether, the alcohol? That requires further testing and analysis. So what you do is you start with all the possible structures, and then you test them to see which one makes more sense from a chemical analysis perspective. In fact, just boiling point alone, which of these two is going to have a higher boiling point? The alcohol or the ether, you think? Now, on Tuesday, remember I said, when oxygen is available, you got some polarity there. So they're both polar, but which do you think is the most polar between the two? Obviously, it's one or the other, right? Which one do you think it is? Who votes for left side? Alcohol. It's okay. I'm not writing names now. Okay. Okay. This is much more polar than this. And the reason has to do with the OH, because the OH does hydrogen bonding. Anytime you hydrogen bond, that's a very strong intermolecular structure. Intermolecular force, I should say. Okay. Another thing about organic chemistry is they have something called functional groups. Functional groups which make the molecule act differently from a chemical perspective. And there's a whole bunch of functional groups. And that's what the 5 units are divided up into, is studying each group, functional group. So what brings alkanes unique is that they have no functional group. They lack a functional group. Okay. This is the pits. If you do it this way, you're going to be so incredibly tired of writing H's and C's for that matter, particularly H's. Hence the line drawings. Now, yesterday, Tuesday, we talked about hydrocarbons. Hydrocarbons are usually typically the first group we study in OChem, and they are only made up of carbon, hydrogen. But there are 3 kinds of hydrocarbons. There is alkanes only have single carbon bonds. Those are called saturated hydrocarbons. When you hear the word saturated, that has to do with hydrogens in there. There are no more hydrogen you can actually bond to that molecule if it's saturated. If it's unsaturated, you've all heard about polyunsaturated oils. Okay, so on the first class, and in this class, the more important class is going to be alkenes. Alkenes are made up of single bonded carbons and double bonded carbons. And they're more unstable than alkanes. So frequently, if you have an alkene, it's susceptible to reactions, degradation reactions, much more so than an alkane. Alkanes are more stable. Alkenes are less stable. So unstable things want to become more stable in the universe. If you're trying to take something that's stable and make it unstable, it requires energy. And we're going to see that particularly in the next subunit when we get into alkenes. Alkynes are that. And we have no alkynes in the body. And since this is an allied health track, I'm not going to spend much time at all on alkynes. We have enough stuff to worry about. So I'm going to de-emphasize that. So when you're going through stuff and there's a question about an alkyne, skip it. Okay, so these are the unsaturated ones. And that would be the saturated. Now, saturated alkanes in your body are less healthy than the unsaturated ones. An example of it, saturated fatty acid would be stearic acid. If you like beef, it's a good source for getting unhealthy fats in your body. If you look at unsaturated fats, the best one is the single double bonded one, which is in olive oil, but it's a little unstable. It's not as stable as stearic acid. And then the worst ones are double carbon bonds, like linoleic acid, for example, corn oil. And then we have another class called omega-3s, and we're going to get into depth big time in our unit on fatty acids. But the omega-3s are particularly important to incorporate in your diet because there's very few places you can get them. You can get them vegetarianly from flaxseed, mostly from fish oil. And I cook a lot. I'm really into cooking. And one of the big deals now are sardines. Sardines are inexpensive and they have a lot of omega-3 fats in them. And you have a huge variety of sardines. If you chose tuna, be very careful because tuna, particularly large tuna, tends to hold a lot of residual mercury. So if you're into tuna, look for skipjack tuna, which are the small tunas. And they haven't lived long enough to collect mercury in their system. Or you can get, and there's some tuna, this is the kind I buy ahi tuna, but it's line caught, and they test every fish for mercury. And it's the only one recognized by the American Pediatric or the American Pregnancy Association as being safe to eat when you're pregnant or breastfeeding. It's a little more expensive, and the taste is much better. You know how awful eating out of a can of tuna is? This kind I buy is really quite good. Okay, so this is gonna be unit 1, and we're gonna be focusing on that in next couple of days. Now, as part of alkenes, there's a subgroup of aromatics under alkenes, and it's called aromatics. And the aromatics have this ring structure. And the benzene ring structure frequently is not written like that. It's written like this. In fact, let me draw that more carefully. So you can draw it either way. One way on the right is much easier to draw, and that's usually the way I draw it. Now, benzene rings are very, very, very stable, even though they're unsaturated. And the reason has to do with the alternating single, double, single, double, single, double. That makes this structure extremely stable. Let me tell you a story. Back when I first started teaching in 1974, I taught at Sacramento High School, and my wife at the time worked at the university in a environmental toxicology lab. And I would always go over there with my classes on field trips. And we would go through the department, and one of the professors, a specialty was in aflatoxins. And aflatoxins are extremely toxic. When you walk in his lab, it smells like bleach because he's always spraying his whole lab with bleach to make sure everything was oxidized. But he used to do this demo for my classes. Now, benzene, again, is very, very, very stable chemically. So he would take a little beaker of benzene and drink it. And everyone was horrified. Horrible lab practice. And he would drink it. And he was saying this is totally safe because it's so stable, it's not going to react with anything. It'll just go straight through my body. And 99.99% of it did, but not all of it. Because benzene is so stable, it can go places that other molecules can't because it doesn't react with anything. So what happens, what does DNA look like? It's a spiral, right? What happens, benzene gets lodged in between the spiral. Now benzene is on the carcinogenic list and parts per billion. So what's safe today may not be safe tomorrow. I can give you a whole bunch of examples of that. So think about that whenever you look on your can of soda or you look on your Cheetos. If you look at Fritos, corn and oil. You look at Cheetos, there must be 30 items on for Cheetos. So just what's safe today may not be safe tomorrow. And by the way, that guy died of cancer, that professor. Okay, so we talked about this on Tuesday, the general formula for non-cyclic alkanes is so this is non-cyclic. And cyclic formula CnH2n. Now, how you put the carbons together frequently will determine its difference in reactivity, its intermolecular forces, and naming. Even though the formula is the same, its structure is going to change it chemically. So if it's long chain, it's abbreviated like this is 5 carbons long, so that's pentane. And with an N in front of it, meaning normal pentane. That means it's a long string, linear string. Branched alkanes have a much shorter backbone, but they have branches off the backbone. So the number of carbons is the same, and the number of hydrogens are the same. It's just the connections aren't the same. Now, the way I do line drawings, I go 1 in my mind. That's where you start. 2, 3, 4. Butane has 4 carbons. So when you start, you just say 1 in your mind and then go. And each time you change direction, the kink, it's a carbon. So this has got a carbon, 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 carbon. Now notice the difference between these guys here. The one on the left is N-butyl. Remember, N stands for normal. That's a long, straight one. Isobutane got the word iso in it. And you can see the structure is different. And there's a lot of subtleties in this branch naming we're going to go through in detail. Another thing about alkanes is they're all single bonded carbons. Single bond carbons can rotate freely. So what happens is how life is, it's going to rotate to the most stable version most of the time. That stable version, notice what the version on the left where the 2 black methyl groups are kind of together. This one here, it twists so the methyl group goes to the bottom, so they're far apart. So what that carbon does, carbon-carbon rotation does, is it minimizes methyl group interference. And the fancy name for that is steric hindrance. So now when we get into reactions, we haven't talked at all about reactions yet. You frequently will get a mixture. And if the mixture combines things that may have a lot of steric hindrance, that's going to be the less stable. And when we have a mixture, you're going to have to circle the one that's most stable. And you have to say why it's the most stable. And generally, there are three reasons for that. One is steric hindrance. And we'll talk in depth about the other two. And it's a stability thing. Purely stability. So with these two models, the one on the right is the least stable because the methyl groups have a lot of steric hindrance. Here, this methyl group is moved around, rotated around, so it's the farthest from this methyl group. Hence, it's maximized the stability by minimizing the steric hindrance. Now, the thing about this part, in the beginning, students find a pain. Okay. So remember when I talked about naming on Tuesday, I said you have to find the longest backbone. You have to find the functional group, and you have to find if there are any branches or not. So the first task is, how do you find the longest chain? Well, we look at the top left one. That's an easy one. Okay, so there are 5 carbons in that chain. How many carbons are in that chain? 5, right? So those are equivalent molecules. Okay, no branching, 5 carbons. Okay, now let's look at the bottom 2. Okay, they have 5 carbons, but what's the longest chain? Well, there's one chain like that. Another chain like that. 4 carbons, either one of them. So the 2 options are equivalent, but it's 4 carbons long, and you have a branch. So let's get rid of the green one for now. And let's go to this guy here. Okay, what are the chains here? Well, we can go like this. That's one. Another, we can go like that. That's another. Or we can go like this. So what's the longest chain of those 3? Four. Yeah. So there's 3 chains here. One is shorter than the other 2. There are 2 4s, 1 3. Okay, so all right, so let's get rid of let's just keep the green one. Okay, now this is a trick. And when you do the first dry lab next week, they're going to give you a lot of these to kind of figure out. And again, you're just going to be running through on backbone chains, which is the longest one that includes the functional group. Now with alkanes, the functional group is H, which there isn't really a functional group. But from unit 2 on, though, there'll always be a functional group. So the longest chain has got to include the functional group, except with alkanes, which doesn't have a functional group. Okay, does this make sense? Why the top two have 5, the bottom one only has 4? The top one has no branching, the bottom one has branching. Okay, now this is crucial when you start naming this stuff. You've got to really pay attention to this, because the amount of carbons on the backbone is going to determine the middle part of the name. The first part of the name is going to determine the branches. The last part of the name is going to determine the functional group every time. Okay, and this is same thing. We just kind of moving everything around. Same with this. What we're doing is moving stuff around, finding longest chain. So these both have a branch. These have no branches. Okay, let's see. Now, we're going to be knowing, oops. The branch names are related to the backbone name, like adjectives are related to nouns. They've got a YL in there. So if you have a base model like methane, which has 1 carbon, if that 1 carbon is a branch, though, it's called methyl, not methane. So the YL means it's a modifier of the original backbone. If it's 2 carbons long, the base molecule is ethane, the branch is called ethyl. And then there's ethyl propyl butyl, it goes on and on and on. When we get into 4 carbon branches, there are a number of these guys. You can have and this is a N-butyl, sec-butyl, isobutyl, and tertiary butyl or T-butyl. And these we're going to talk a lot about. You're going to have a chart you're going to be using a lot. And after a while, you'll automatically memorize it. You can also have non-carbon branches as well. Now, there's a list of them that we'll be using, and we have no fluorine in our body unless you are brushing your teeth with fluoridated toothpaste. There's no fluoride introduced into your body, or if it's not in the water. I grew up in Texas, and they fluoridated the water all over the place. Fluorinated water also stains your teeth. So there's a toss-up between, you want to deal with cavities all your life, or do you want to deal with pretty white teeth? Well, so the ones I want you to know are fluorine, nitro, and amino. Now, these don't worry about until we get to the chapter on amines. But we're going to be using, I should count bromo too here. So for now, I want you to know those two. And those basically are branches. They're a non-carbon branch. They're a branch. So for example, if we had okay, so start off with 4-carbon backbone, one carbon branch, and a chloro branch. So how would we name this? We can do one more chart here. Okay, so from Tuesday, remember again, 3 parts. The middle one is the backbone. The one on the far right is the functional group name. The one on the left is branching. Okay. These are the prefixes you need to know. Now, the one that I is kind of interesting is the 4. And they name tetra for 4, but they mainly use it 99.999% of the time when they're naming the number of branches. So if there are 4 methyl branches, they'll go tetramethyl. If it's a backbone, they don't call it tetra, they call it buta. Okay, so let's look at this molecule here. Okay, so it's got it's got a 4-carbon backbone, right? So that is a buta. Functional group is a hydrocarbon, so that's the functional group name. However, we have 2 branches. We have a chloro branch, we have a methyl branch. Okay, so this is 1 carbon long branches are called methyl. So that's what this is. So we have to number the backbone because we have to determine where the branches are located on the backbone. So we can start numbering from left to right, right to left. So let's number from left to right first. And then right to left. That means we're going to get 2 names. We're going to get a name for left to right. We're going to get a name right to left. So let's do the left to right one first. Okay, so the chloro is on carbon number 2, and the methyl is on carbon number 3. So 2-chloro, 3-methyl butane would be one name. If we went from right to left, we'd have 2-methyl. So in this case, and for our class, you put it this way, there is a huge class you can take on naming, a whole semester. And they will take this and say one is more accurate than the other, or more, I should say more correct. Our class is the main thing, what I want you to get out of here is that if we look at the numbers, 2 plus 3 is 5, 2 plus 3 is 5. So those branching numbers are equivalent. Normally, if the branching numbers are lower, that's the one you choose, but here they're equivalent. So what we would do is I would accept either one, except the bottom one has a problem. Can anyone come up with a reason the bottom one may have a problem? It has to do with alphabetizing. They always want to alphabetize left to right. So really, it should be 3-chloro, 2-methyl. And by the way, this is the one that's officially accepted, but this one will be fine for our class as well. Now, the first test, you're going to have a lot of naming on it, but every test you'll have three things: naming, reactions, and intermolecular forces, every test. Okay, does that make sense where I got how I constructed this name? Step number one, backbone, yeah. Yeah, one is your dry lab. That's going to be one giant worksheet. And then I have much more worksheets as well. In fact, okay, her question had to do with, are we going to have worksheets to practice this? One, your textbooks got a lot of example problems as well. But if you go to, if you go to Files, Unit 1, Worksheets, you'll find a few practice problems. Okay? These are all worksheets for Unit 1. So there's no reason you don't have adequate practice. And these all have answers too, by the way. Now, I'll frequently be going over some of these worksheets at part of lecture as well, just as example problems. But there's lots and lots and lots of practice. Now, this Unit 1 has a few more worksheets because it covers more material, because this is a 3-unit class as opposed to a 5-unit class, because this covered aldehydes and ketones and carbohydrates as well. So this first test is going to be only on alkanes, alkenes, and alcohols. Alcohols, ethers. That's it. Very, very focused first test. And I think at first you're going to think it's hard, but you'll find it's the easiest test. After you do Unit 3 and Unit 4, you'll go, oh my God, that first test was so easy. I can do this in my sleep. Okay, so you know how to find the worksheets now, right? Okay, this now, are these two different molecules? These guys here? That's right. She says no. Why? Got to be one or the other, right? Yes or no? Remember that modality of tumbling? The top one's just a tumbled version of the bottom. So the branching is done on the second carbon in on both of them. So that's the second carbon. As you're going from left to right. If you're going right to left, it's still number 2. So these are just the same molecule tumbled in space. So let's name these, okay? So you've got a branch on carbon number 2. It's going to be 1, 2, 3, 4, 5. So the backbone is 5. The branch or the functional group is an alkane, so it's just an E. And we have a branch on carbon number 2. So that's 2-methyl pentane. Now, if you number incorrectly, the answer is going to be 4-methylpentane. So we have 2-methylpentane, 4-methylpentane. 2 is less than 4. More hot math in this class. So the 2-methyl pentane is the more correct one. All right, so let's look at this guy here. Okay, and the yellow is the backbone, 7 carbons long. And we have 3 branches not on the that come off of the backbone. We have a methyl, and when you look up in the table, you'll find that this 3-carbon configuration is called isopropyl. Okay, so first step is hepta identifies 7 carbons, E for alkane functional group, and then we have to deal with these branches. And we can number from left to right or right to left. If we number from left to right, we're looking at 2 methyls, and what carbons of those are on? 2 and 3. So that's 2,3 dimethyl 4 isopropyl heptane. Now the question is, what comes first, isopropyl or methyl? Now you have to ignore the iso. You're looking at, you have to ignore the di. So really we're looking at M versus I. Which would come first alphabetically? I. So that means the isopropyl has to come before the methyls. So the real answer is, no, it's right here. Now, on a test, if I was asking you a specific naming question, and if you put the isopropyl second, methyl first, because you're thinking the di, I would ding you for it. But if it's on a, all reactions require naming. Reactions are in 2 parts. There's the reactants and products. You have to name the reactants and you have to name the products in the IUPAC way. So if you're naming this in a reaction and you put isopropyl 2,3-dimethyl heptane, I wouldn't ding you for it. But if it was for a naming question, I would. Because in a reaction, the reaction is the more important part of all that. You may get a sad face, but that I wouldn't take off any points. Okay, now I did mention we can have cyclic versions of all this as well. Okay, the most stable of the cyclic carbon compounds, including oxygen or nitrogen in it, are 6-sided, the hexa 6-sided circle. We're going to find this in carbohydrates. Carbohydrates spend most of their time in the cyclic form. They open up, but most of the time it's in a cyclic version. And even if it has nitrogen or oxygen, it's still the 6-sided figure is the most stable. And then close to that, though, is 5-sided. And you can go 7-sided and 8-sided and all this other stuff. But the 6 is by far the most common. And the reason why it's the most common is because it's the most stable. The angles in the carbon are perfect if it's 6 carbons. They're not stressed at all. As soon as you get away from 6 carbons, the angles are forced and they're not as stable. That's why the 6 is the most stable, because the angles are not stressed at all. So for a 6-sided structure, is going to be cyclohexane, cyclopentane, cyclobutane, cyclopropane. This is really, really unstable. Those bonds have to be really stretched, and it's just not very, very conducive to the perfect alignment of carbon. So in a ball and stick model, we were putting these together with models. That's what they look like. And in fact, when you put them together with models, the cyclopropane is really hard to put together with a model, because a model reflects the perfect 109.5 degrees. And this requires something significantly more strain than that. Okay, so whenever we talk about naming cycloalkanes, that's going to be the backbone. So as soon as you have a cyclic in there, that automatically determines backbone. Okay. So this here, we're not going to go 1, 2, 3, 4, 5 as far as the longest chain, because it's cyclic. That means that's automatically the backbone. In this case, we've got two branches off the cyclic backbone. One an ethyl group, 2 carbons, one's a methyl group. So that's what that looks like. So 3 parts again. So we're going to have cyclopenta. Functional group is E for ane, and we have 2 branches. We have an ethyl group. Now you can number 2 ways. You can name left to right, right to left. So if we name it from the ethyl first, because E comes before M, so we have 1 ethyl, 3 methyl, cyclopentane. The other way, if we use the other numbering screen, we'd have three ethyl, 1 methyl, cyclopentane. The bottom one is the preferred one, because it starts with a lower number. But the main thing, as soon as you cycle, you automatically know the backbone. Boom. Okay, so sometimes we can have something called geometric isomers. That means the basic structure looks the same, except there's a slight difference. Who's heard of trans fats? No one's heard of trans fats. Are they good for you or bad for you? That's right. They're bad for you. What are the good fats? What's the opposite of trans? Cis. So the cis fats, they never refer to them as cis fats. They always say trans fats are bad, and they are bad. Now, the problem is whenever you have, remember we talked about single carbon, they freely rotate. When they're cyclic, they don't do that. They're restricted. So as soon as you see restriction, either with a double bond, get into the next subunit, a double bond or cyclic, think in your head, restriction. Because that will mean that there's a possibility of a geometric isomer, a cis or trans geometric isomer. So and the reason for that is there's no more free rotation. Free rotation allows you to get rid of that, okay? So if we look at these two molecules here, okay, one, they're cyclic. Up, red flag goes up. Is there a geometric isomer possibility here? And the possibility is having to do with these methyl branches. Because they aren't freely rotating, they're stuck in either that position or stuck in that position. Now, when we get into biochemistry, we're going to find that there are enzymes that modify this. They're called isomerases. And those isomerases actually can modify this. But until we get to that, we're in a test tube environment now, not a biological environment. This guy here, formula is the same, structure is the same. We have branching on these two carbons, same branching on these two carbons, but they're not the same. Not the same. Now, this comes up in health all the time. MSG, for example, monosodium glutamate. That's based on the amino acid glutamic acid, and we make it naturally. We make one form of it. And there are two forms of that. One makes food taste good. The other one does nothing. And the one that the other one does are the ones that people have allergies to and reactions to. Like I have a good friend who went out to dinner last night, and she can't do MSG because she has a problem with the R version of the MSG, not the natural version. Because I use MSG a lot, and it doesn't affect me a bit. Food tastes better with it, so I use it. There's another problem. Who's heard of the thalidomide back in the 60s problem? Thalidomide was given to new mothers for anti-nausea and during the first trimester. The problem with it is they didn't separate the D and the L form of thalidomide. The L form was anti-nauseous. The D form causes birth defects. It's a teratogen. And these poor babies were born with no arms and no legs. And it was very widespread in the early 60s, particularly in Europe. And that's the only difference. Look at the formula, and the difference is left versus right. What's the difference between these two? 5 fingers, 1 palm. The 4 fingers and the thumb are attached to the palm. 4 fingers, thumb are attached to the palm. But are these the same thing? If you're left-handed, pick up a right-handed pair of scissors and try to use it. They're different. And that was the thalidomide problem and the MSG problem as well. So this subtle difference is a big deal. So right away you go up, cyclic, restriction. What does that mean? It means if there are any branches now, those branches can be in a cis relationship or they can be in a trans relationship. And you have to specify. So what I was if you're writing out the name for these, notice in the beginning, you have to specify cis or trans. And always cis are together. Think of sister, cis. Now this comes to play a lot in biological molecules. And we already talked about fatty acids being cis and trans. In the eyes, when you see stuff, there's a molecule in your eye that's modified from cis to trans. It comes up a lot. Comes up a lot. Now, you have to have a situation where you've got branching next to one another. If you have no branching, if it was just a plain old molecule that looks like this, that's cyclic, but there's no branching. So if there's no branching, there's no cis or trans. Okay, IMFs. Non-polar molecules. There's no oxygen or sulfur or nitrogen in there. Just carbons and hydrogens. That means it's non-polar. Very low intermolecular forces. Hence, it's got a low boiling point, low melting point, and low surface tension. So if you look at this, starting with a 1 carbon up to a 10 carbon hydrocarbon, you can see the melting point varies. They keep going up. So they have the same IMFs. These all have the same. So what's different about them is they just weigh more. The molar masses are greater. Hence, the boiling point will go up, melting point will go up as you get more mass. But the IMFs remain the same. And we're going to see this graph a lot with different functional groups. This functional group, when we finally get to the ones with multiple functional groups, I'm going to be writing on this one alkanes and alkenes. And you'll see some with alcohols, aldehydes, ketones, carboxylic acids. And you can see, and it's an intermolecular force difference between each classes. And that's what will affect the boiling point, melting point, et cetera. Okay. All right. So we've covered naming. We've covered intermolecular forces. Now, lastly, we're going to start getting into reactions. We haven't talked about reactions at all. This is the part that everyone hates in this class, are reactions. I've been doing this since 15 years, whatever that is. And every single class, no exceptions, they all hate reactions. So this needs lots of practice. Okay, so as a review here, no test next week. Now, this is super review from 305. You start with reactants, things happen, you end up with product. In this class, we're going to have one more additional thing, and that's called conditions. Always 3 parts. The conditions change, the reaction may or may not go. For example, if I have a piece of paper here, okay, cellulose in the paper, oxygen in the air. We have combustion, right? Why doesn't the paper explode into fire? As you all know, paper burns and it needs oxygen to burn, but why doesn't it just burn? Huh? It could use a catalyst, but what else does it need? Heat. No heat, no combustion. So if we change the conditions by adding heat, things happen. If we don't change the conditions, nothing happens. So conditions are required for all reactions. Now, if we look at a graph of potential energy, and we start with reactants, the reactants are going to have a certain amount of potential energy. Products are going to have a certain amount of potential energy, lower than reactants. Okay, real important, lower. Lower than reactants. Because high potential energy is unstable compared to low potential energy. So in the universe, there's one little caveat in all this, it's called entropy, but we're not going to talk about this class. But things go from high potential energy to low potential energy, just like this. High potential energy, it doesn't go up, it goes down. Why does it go down? Because it's lower potential energy down there than up here. Reactions are the same way. Potential energy is stored in chemical bonds, though, not position like this was. Now, she mentioned we needed something called heat, and that's to get us over that hump. That's what the conditions do, gets us over that hump. There's a fancy name for that hump. Fancy name for that hump is called the activation energy. High activation energy means it needs a lot of energy. Low activation energy means it's a little bit. And that brings up your point about catalysts. So what a catalyst does is it lowers the activation energy, so there's not as much energy being required for the reaction to happen. Now, I remember when I was interviewing for a job, chemistry job, one of the questions was, tell us about diamonds and graphite. Now, graphite looks like charcoal. You all know what diamonds look like. There's these gorgeous crystalline things, all kinds of reflections and stuff. Same thing, pure carbon, carbon. Guess which one's more stable? That'll be one of the two. The graphite is more stable. So you ask yourself, I just spent $10,000 on a ring. It's going to turn to charcoal? It will in a couple of million years because the reaction is really slow. And the reason why it's slow is it has a huge activation energy. But in reality, the diamond is less stable than the charcoal. So there's two things working here. There's kinetics, speed at which the reaction happens, and also how stable it is. Okay, so what happens when we have a reaction? Okay. Okay, first thing, we need to break up the bonds in the reactants. That's done by the activation energy. So instead of a nice molecule, it's all broken up in little pieces. And right there is the mix. That's called the activated complex. Activated because we've applied activation energy to it. So all those break up. Now, which is more stable? Well, remember, high potential energy is not stable as opposed to low potential energy. Well, there's two pathways for lower potential energy. We can go to the left or we can go to the right. So what happens is some reactants are reformed and others go to products. You always have a mixture of beginning stuff and ending stuff, always. And it depends on a bunch of factors. How much more stable is the end product versus what you're starting with? What's the activation energy? Blah, 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 blah. A whole bunch of little variables there. Okay, so this is kind of what happens in a reaction. Start with potential energy reactants, certain level, then you go to a lower product potential energy, and you go via the activation complex. And that complex can be really, really high or can be really, really low. We're going to find when we get into biochemistry, enzymes or something called organic catalysts. And catalyst lowers the activation energy. So things go much smoother. Now, this idea of combustion, how does our body get energy? If we were a plant, how do we get energy? From the sun, right? Okay, we can't get energy from the sun. We have to eat plants or animals to get our energy. So where does our energy come from? Food. Yeah. So when we get energy, it's stored in our body whenever we need it. There's quick burning, medium burning, and long-term burning. And we're going to talk a lot about this. Now, the problem is this process generates energy. Just like that piece of paper on the counter here. That combustion produces energy. Put your hand on it, it gets hot. Well, our body, that is not a very good process for our body. So what our body does, it does the same exact same thing. It takes our food, whether it's carb, fat, or protein, burns all of them and forms an energy molecule called adenosine triphosphate, or ATP. But it does it in a really safe way in about 18 steps instead of one step like with the paper. And it's done via catalyst, organic catalysts or enzymes. Okay, so for alkanes, there are two reactions. One's combustion, and the other is halogenation. Okay, halogenation is when we add a halogen. Halogens are group 7, starting with fluorine, chlorine, bromine. Now we're not worrying about fluorine. The main two are chlorine and bromine. So how do we add those to an alkane? So let's take an alkane like propane. We're going to add to that chlorine gas. So what we're going to end up with is a halogenated propane. And we're going to get a mixture. Because statistically, it'll add in the middle or add on the end. So we have three parts. We have to name the reactants. So one of the reactants is propane. Another is and the conditions, UV and heat. So you can have chlorine gas and propane, nothing will happen. When we start heating it up, then the chlorine starts adding to the hydrocarbon. So we end up with into 2-chloropropane, 1-chloropropane. So if I gave you this reaction over here, I said, how do you make that? This is what you put down. You put down propane plus chlorine gas, arrow. Above the arrow are the conditions. In this case, it's UV and heat. Gives you these. Now, this is a mixed product. And we're going to talk about which is more stable between these two. There are two governing factors, symmetry and something called Karnoff's law that we'll talk about a little later. But whenever you get a mixture, you have to circle the one that's more stable. And in this case, symmetry wins out. The one on the left is more symmetrical than one on the right, so it's going to be predominating. So what you do, you'd circle it, and we're going to get into this in more detail, but basically you'd circle it and you'd say symmetry. Okay, so that's your first reaction. Now I'm going to show you a flow chart I've made up a long time ago, which got all the reactions in it. So you'd have to know the reactions from the flow chart. You need to know how to set up the reactions, starting with reactants and products, and then conditions. That'll all be in the flow chart. Okay, does this make sense? First reaction. Now, hydrocarbons, I should say, alkanes are pretty stable. So there are very few reactions, only two. Okay, and the second one is going to be combustion. So let's take the same propane. So when it undergoes combustion, it combines with oxygen. So the conditions are oxygen plus spark, or an energy source. And you always get carbon dioxide and water. And this is almost all hydrocarbons. Let me back up. Most organic molecules burn or undergo combustion. Okay, so you have two reactions now. Two reactions. Halogenation, usually with chlorine, sometimes with bromine, and combustion. So that's kind of it for alkanes, but we need to practice a lot. Now, the things we need to practice on alkanes are naming and reactions. Now your dry lab 1 focuses on alkanes. It's a good solid 2.5 hours worksheets. And I'll be there. And remember your dry lab, you don't have to have goggles or a lab coat. By the way, I have 2 additional lab coats that are up for grabs. They're both larges. So if you're in the Tuesday lab, come on up. If you're interested in those lab coats, come on up and I can show you them. And if you like them, take them. And for Thursday, folks, same thing. I got 4 lab coats, 2 on the smallish side and 2 larges. And you're more than welcome. The 2 small ones need to be washed. The 2 large ones, I think, have been washed already. But I would wash them anyway. Okay, so I'm going to stop here for a second. Now, right here, it says Unit 1 reactions. This I would suggest when you get home, print off. Now, these are the reactions for Unit 1. We've only done the top one today. So if you want to end up with a halogenated alkane, what do you start with? Well, the halogen. If you want a chlorinated hydrocarbon, you start with chlorine gas, UV or heat, boom. If you apply a spark to it, you'll end up with a combustion reaction. So I have, and you're free to include with your tests. You don't have to memorize this, but I want you to get used to using it. You'll be using these throughout the whole semester, particularly in units 1 through 4. I noticed with an alkene, there's a lot more concoctions that can go on with an alkene. That's because it's less stable than an alkane. Alkanes are nice and stable, hence they don't have very many reactions. Okay, so that's called Unit 1 reactions. Definitely print that off. So that's under Unit 1 files. Okay, so let's try practicing these reactions. Say I have ethane, 2 carbons. Throw in some chlorine gas. What else do I need for anything to happen? Remember, all reactions have 3 parts: reactants, products, conditions. What do I need for this something to happen here? Remember from up here? Oops, I'm sorry. I need UV and heat. Then we're going to end up chlorinating that ethane too. So this is going to be okay. So 3 parts. The branch is chloro. Backbone is 2 carbons. The functional group is E, or an alkane. That would be 1 chloroethane. Can I get 2 chloroethane out of this? This is a trick question. Well, what does 2 chloroethane look like? Well, 2 chloroethane, I keep hitting that table. What's the difference between 1 chloroethane and 2 chloroethane? Or is there no difference? Right, there is no difference. So you only get 1 product, 1 chloroethane. If you tumble one on the left, it's going to look like the one on the right. That means it's the same molecule. The tumbling gives you the same molecule. There's no difference. So no mixture. If you have more than 2 carbons, you will get a mixture, like we mentioned before. So let's do that one again. Start with propane, chlorine gas, heat and V. Now we're going to get a mixture again, because it's more than 2 carbons. Because this one does not look like this one. So we have to name them. This would be 1 chloropropane, 2 chloropropane. Sorry about my handwriting, you guys. Whenever you have a mixture, you got to circle the one that's more stable. And this is symmetrical. If we had 1 carbon, like we started with methane, for example, we'd end up with chloromethane and no mixture. So whenever the number of carbons, I get this every time. So whenever we get over three or more carbon, then look for mixtures. If it's 2 or 1, no mixture. Okay, so we have, what are we starting with? We're starting with methane and chlorine gas. What are the conditions? I forgot to put the conditions on there. That's heat or UV. And then I have the product, chloromethane. 100% of the points in that problem. All reaction problems are like this. Now, the tricky part of a reaction is you can have multi-step reactions. Like we mentioned about taking food and combusting in our body to adenosine triphosphate energy molecules. There are like 19 of those steps to get there. A bunch of enzymes, and you go through glycolysis, the Krebs cycle, electron transport to get there. All those have a zillion reactions because we do it all at low temperature, 98.6. You don't do it at 200 or 300 degrees. Okay, do you see the essence of what a reaction is, what I'm looking for in this? And you're going to have ample opportunity to practice. All right, let's do a combustion problem. Okay. So we have oxygen present and a spark. What do we always get? Carbon dioxide and water. And you don't have to label the water. It's okay. You can if you want to be nice and complete. Okay, we got to name the reactant though. Okay, so this is a branched chain hydrocarbon. So let's look here. Backbone is 4 carbons long. And we have a branch. So that's going to be, if we go from left to right, that branch will be at 2. If we go right to left, it'll be at 3. So 2's more or less than 3. So we're going to use the left to right. So that's going to be backbone is 4. That means that's a butane. And then the 1 carbon branch is on carbon number 2. So that's going to be 2-methyl butane. Plus oxygen and a spark, we end up with carbon dioxide and water. So those are the 2 main reactions for alkanes. Super simple. Okay, so are there any questions about any of this stuff and reactions? Are there any confusing parts? Good. All right. Let's do a couple more reactions. I'm going to call it good. Now, there's one version of reactions. I give you reactants, and I'll tell you what you make. The other way is I'm going to tell you how to, if I want to make this product, how do I make it? How do I make that? The reactions we studied so far. Well, it's chlorinated, right? That means we're going to be needing chlorinated gas on something to get there. So most of the time, except for our 3rd subunit, the backbones will remain the same. So what is our backbone on the product here? Well, we've got 1, 2, 3, 4. So it's a 4-carbon backbone. That means we're going to start with a 4-carbon backbone. And then we're going to add to it chlorine gas, heat, and UV. So when I ask you, how do you make this? Then back up. So during reactions, you're going to be going forward and backwards. Forward means I give you stuff, I throw in some conditions. What do you make? Going the other way is I'll ask you, how do you make this? And you're going to go backwards. And what I'd recommend you do is you duplicate the backbone. And we got to name reactants and products and conditions. So the reactants is 1, 2, 3, 4. So that's butane. And the product is, what is the product name going to be? And I have butane in it, but what's the numbering system we're going to be using? Well, you can come up with 2 names for this. One name is 1-chloro butane. The other is 4-chloro butane. Which is better? 1 chloro or 4 chloro? 1. 1 is better. Okay. So that's what I would want to see is this on the left side stuff. And of course, you've got to name it, name conditions, name product, name reactants. Everyone okay with that? Okay, I tell you what, let's end this today. But I encourage you when you get home to print this off. You'll find that, notice you start with an alkene, you end up with a spark. You start with an alcohol spark. All these, combustion is a very common reaction among organic compounds. So basically, any organic compound you can undergo combustion with oxygen and the spark. Okay. Are there any last minute questions about administrative stuff? How I grade? By the way, I do ground. So to get an A in this class, you need 89.5 on 90, because 89.5 rounds to 90. 79.5 for B, 69.5, etc. Okay, I always ask that. Yeah.
The students getting the cardboard to do their project.
Where?
Mhm.
Walmart,
You know,
Michael's. It's all over the place. It's a three panel poster. Yeah, and they're about this high. And think scrapbooking techniques. Handy stuff, you know. My one class in Olympia, the one that wanted to present the whole class, they did blinking neon lights.
but you have the rubric in the file.
Yeah, go to files project. So what'd you do in the Army?
Oh, the health inspector.
Oh, let me end this recording here.